With the exploration and human habitation of Mars on the horizon, how would we travel, transport materials and people, and further explore on Mars? Our answer is hypersonic flight, because it will allow us to travel great distances without the need for large supporting transportation infrastructure, which would require massive amounts of material, time, and money. So, if we wanted to reach hypersonic speeds on Mars, what would we need to change? First, let's begin by looking at a typical airliner. When flying, this airplane experiences four main aerodynamic forces: lift, drag, weight, and thrust.
Right now, our airplane is flying at 230 meters per second, or 515 miles per hour. That's pretty fast. So why don't we just put our airplane on Mars and see what happens? Well, what gives? Well, the four aerodynamic forces will change. Weight, lift, and drag will decrease, and we lost all of our thrust. Why does this happen? The weight will be smaller because Mars's gravity is only 38% of Earth's. But the more important question to begin with is, why don't we have any thrust?
Most airplane engines are air-breathing, meaning they need oxygen to operate. This isn't going to work as the Martian atmosphere is comprised of carbon dioxide. So, what could we use instead? By using a rocket engine such as what was used on the X-15, a hypersonic aircraft tested in the 60s, we can easily solve this issue. This lets us store liquid fuel and oxygen on board the airplane. Depending on what fuel is used, it can even be produced on Mars, such as ammonia. This would make our plane go very fast and reach hypersonic speeds. But what exactly does hypersonic mean?
Hypersonic is generally defined at speeds 5 times the speed of sound, or Mach 5. However, this is not the full story. Hypersonics is when certain physical phenomena become more important with increasing Mach number. These complex phenomena are important considerations to the designer of the hypersonic aircraft. When objects travel at hypersonic speeds, they generate shock waves, which are strong pressure waves that occur when an object moves faster than the speed of sound. Hypersonic aircraft fly high in the air, even higher than our aircraft. They do this because the air density, pressure, and temperature is much lower, even comparable to the Martian atmosphere.
At sea level on Mars, the pressure and density is less than 2% of Earth's. This is like being 30 kilometers in the air on Earth, and it will get even thinner as we increase our altitude on Mars. While this doesn't affect the thrust of our rocket engine, this will affect our lift and drag. Lift and drag both depend on the air density, how fast the aircraft is flying, the size of the wing, and an experimental coefficient.
Due to the lower density of the Martian atmosphere, the generated lift drops tremendously, so we need to compensate for this by increasing the other parameters. Ingenuity faced this exact issue. NASA's solution to this problem was using massive blades that spun extremely fast. This simple but effective solution solves the lift problem but does not allow Ingenuity to travel very far or fast. With our airplane, we can solve our lift issue by flying at hypersonic speeds. Since lift increases exponentially with velocity, our lift problem is solved with sheer speed. Well, we should already achieve this with our new rocket engine, so let's try to fly again. Oh no, what happened now? Well, if we look back at drag, we can see that it also exponentially increases with velocity. Not only that, but do you remember those shock waves? That's what we're experiencing, so let's investigate this. As opposed to standard airplanes with streamlined wings, hypersonic aircraft are designed with sharp, thin wings that look like diamonds or wedges. They are designed like this because they optimize the shock waves, which in turn minimizes drag. Another interesting aircraft design is called a delta wing, where the wing shape is a triangle. This design provides large lift generation because the whole plane becomes the lifting surface. So, let us modify our aircraft. With our new design for our Martian aircraft, we have less drag and more than adequate lift, allowing us to sustain hypersonic flight.
That only leaves us with controlling our new hypersonic airplane, taking off, and landing. Control systems are similar in hypersonics, so we can continue to have flaps, ailerons, elevators, and rudders, just like what's found on conventional airplanes. But with a thinner atmosphere, we could also make use of reaction rockets to help stabilize and control the aircraft. As for takeoff and landing, we just need a much larger runway to allow the airplane to take off and land at higher speeds than on Earth.
Will our final design be able to sustain hypersonic flight? Well, maybe. Hypersonics is a very complex and exciting field, and we have only scratched the surface in this challenge. With the help of the newer generation of aerospace students, we will one day see a hypersonic airplane on Mars, expanding humanity's horizon forever.